I'm presenting joint work together with my students, Emil and Gregers, who unfortunately couldn't be here, so I'll present the paper on their behalf as well. So the title is a bit of a mouthful, so let me turn it into a bit pieces to start with. So the paper presents a reactive programming language, and I'll tell a bit more about what that means. And it uses a modal type system to do so. So using types inspired by modal logic, in particular temporal logic. And with this language, we can build asynchronous systems. And finally, we have implemented this language as an embedded language in Haskell, which comes with its own set of challenges. So let me start at the top. So what is reactive programming? So you can think of a reactive program as a program that sort of runs continuously, and it continuously gets input from the context, from the environment, processes in some way, right? So it traverses the data through here, and then in the end it produces output, but also continuously, right? It runs continuously. So you can think of it as for example, a robot, right? So that receives input from its sensors and then reacts accordingly by sending instructions to the motors to make the robot run, right? So that would be an example of a synchronous system, right? Because you get synchronous input from the sensors by some kind of sampling rate. An asynchronous example would be a GUI, where the GUI runs continuously, receives input from the user, and then reacts to those inputs from the user continuously, right? As the user presses button, writes text into text fields, and so on. So this is what you can think of as a reactive program. And what we want to do is we want to program these things in a functional setting, right? Using functional programs. And so these boxes here, these are now signals, right? So you can really think of these things as functions from times to values, right? So here is a signal float. So this is really a function from time to floating point numbers. And we want to manipulate these signals as we also manipulate high-order functions in function programs, right? So we want to compose them, manipulate them, and so on. Right, so let's give an example for this. So I just give names for all of the inputs, x, y, and z, and all the outputs, and this is how a functional program, a function reactive program might look like, right? Where we combine the signals x and y using the zip width high-order function, right? That we give a function as an argument here, the plus that combines the two signals, right? And B here is defined as using the map function, higher order map function, right? So this is kind of the programming model that we're considering. But we have to be careful when we're designing such a language, right? So if we're not careful, we might be able to write programs we rather shouldn't. So that can be defective in at least two ways, right? That are either not causal, so we might be able to define signals whose value now might depend on another signal's value tomorrow, right? They're not good. We cannot actually run these programs. And secondly, reasoning about memory is very difficult, but it's a very high-level programming style. So it's very easy in this sort of high-level compositional programming style to consume more memory as the program runs, right? So eventually the program will just run out of memory and will stop, right? So we have to be very careful about this. And so there's a couple of ways to avoid these problems. And a particular elegant one is using types. So it was first proposed by Neil Krishnaswamy a decade ago now, and that uses an idea sort of drawn from linear time logic using this modal type operator, this circle here, which we pronounce later. And we use this to sort of capture the passage of time. So how does data pass through our system over time? And so now we can express a type like this later A here, right? So that says now, this says now we have data of type A, but it's not necessarily available now, but in the next time step. Right? So we can make more precise statements about when data is available. And now we can define our type of signals like this. Right? So it's a recursive type that says a signal of type A consists of a current value of type A, and then in the next time step we get the future state of the signal, right? And if you unfold this recursive definition, you really see how time goes on, right? We start out with a value of type A now, and then in the next time step we get a new value of type A, and in the next time step we get the next new value of the signal of type A, and so on and so on. But so here I talk about the next time step, right? So we need some clock that tells us, well, when does the next piece of data arrive, right? And in this system, this is a global clock, so all signals work according to this global clock, right? So all signals are synchronized so that they also interact in this way, right? And this works well, for example, in the robot, we can program these things using a synchronized system, no problem. But what if we want to actually build GUIs where we have to deal with asynchronous input streams? Right, so how do we make this all asynchronous? And there's different approaches, and here I'm going to show you a particular version of this. And it was presented last year by a colleague of mine, Rasmus and myself. And the idea is to have this later modality, the circle, to have an additional component that tells us something about the timing information. So intuitively what this means, now a value of type later A now consists of two components. Right? It consists still of a value of type A that is available at some point in the future, but it also consists of this clock theta that tells us when this future actually will arrive. Right? So there's this explicitly in its value also this timing information. And so now we have to have some introduction and elimination form to interact with this later modality. Right, so we have this delay that tells us that allows us to move a computation t of type A into the future according to some clock theta. Right? It says, please evaluate t as soon as this clock theta ticks. Right? And then conversely, we can observe a delayed computation like this using advance. Right? So given a delayed computation t of type later A, we can turn it into its value of type A, assuming that we know that the underlying clock has ticked, right? We have to be careful about this. And this is why we have these additional things in the context here, these tokens, that tell us something about the timing information, right? So the way that you can read this is, so normally in the context, right, we only have typing information about variables having a particular type, X has type A and so on. But now we also have this timing information in the context here. So this here, this tick of theta means that a single time step has passed on this particular clock theta, right? And so this is a sort of evidence that this time has passed. And t can now use this information, right? And it makes sense because down here we say, well, delay t until theta has ticked. So we know that as soon as t is actually evaluated, t must have ticked, right? Otherwise, it wouldn't have. So we can use this information. So we have this evidence available to us. And we can use this evidence then to call advance, because we can only advance the term t if we know that the underlying clock, so this is the clock here of t, that has ticked. And here we say, oh, we have to have this evidence in the context. Right, so here this typing system makes sure that we interact with this later modality in the right way. So we avoid this problem of non-causality and also time leaks. All right, so there's a very brief way of telling you about this type system. So let's see this in practice. So here is this example of a signal that we define, again, as before, as a recursive data type, now using this new modality, this asynchronous modality. And we can implement this increment function. It takes a signal of integers and returns a new signal where we have incremented the value. How do we do that? Well, we decompose the signal into its head of type int and its tail of type later signal of int, right? And then what we do is we construct a new signal. It has, again, a head that we increment. So it's x plus 1. And then here, this has to be something of type later of signal of int, right? So first we start out with delaying the computation, and then we recursively call our increment function. But increment takes as an argument a signal of integers. So we have to first turn this xs here from type later of signal integers to to just a signal of integers, right? So we have to remove the delay, the later modality, and that's why we have the advance here. Right? So here we can sort of see how delay and advance interact. And we can do this advance because we have delayed according to the clock of this delayed signal. All right, so this is how we interact with this later modality. Okay, so now how do we do all of this in Haskell? Right? How do we implement a language like this as an embedded language in Haskell? And so traditionally, if you look at implementation of FRP languages, these are typically shallowly embedded, right? So that allows you to have seamless integration with the whole software ecosystem without any kind of extra syntactic overhead or marshalling. Right? You have systems like Yamper that ensures all these nice properties about your FRP program using only signal functions as primitives. You cannot directly manipulate signals, but only sort of construct signal functions. And another library is FRP Now, and what they do is they sort of only give you a sort of careful selection of combinators to construct and combine these signals. Here, things are a bit more difficult. Right? So here we are relying on the type system to ensure that our programs are well formed and don't go wrong in a temporal sense. So it's not easy to embed this as a sort of shallow embedding in a host language. In particular, we don't have typing rule like this, which might seem silly, right? So this says what we would expect is that if we have a variable of type A in the context, then we better be able to use it, right? But this X might actually refer to a value from the future, right? So we shouldn't be allowed to use it necessarily, right? Because we would risk having a non-causal system. Or it might refer to a value from the past, right? So if we use it, we run the risk of introducing a memory leak. So we have to be very careful about this. So this is one issue. Another issue is that all this clocking information that I told you about, right? When we delay a computation, we have to say according to which clock we want to delay. Now, in this example I showed you, the programmer has to do this explicitly, which is a bit tedious. So we don't want the programmer to actually do this in practice. So we need to find a way to do this. So that's what we did in this implementation of a language that we call Async Rattus. So this is based on this calculus called Async Rat that I mentioned earlier. And so it does it in sort of in two parts. So the language consists of an actual library that gives all the combinators for example, the delay and advance to interact with the modality. But it also needs something extra. There's a compiler plugin that does all the extra parts that is required by the type system. So it does these two things. First of all, it checks. So the compiler plugin has access to the AST, to the Haskell syntax tree, right? And so it can check the type system of Async Rattus. So it has additional checks. And secondly, it also infers these clocks, these clock annotations, right? So and they're inserted automatically by the system. So it is some form of program elaboration that is done by the compiler plugin. Okay, let me show how the language works. This is here the very simple example of the increment function written as Async Rattus. So this is just a normal Haskell file, .hs, and the only thing that you have to be careful about is that you have to have this magic incantation at the beginning that enables the compiler plugin, right? So that we've written. And so now everything in this module is Async Rattus. And then first you import the actual language. So the first import says, okay, import the syntax of the language, so you have access to advance and delay. And then the second one imports the signal processing library, so we now can work with signals, right? And down here we implement the increment function that I showed you earlier. And here this is really a shallow embedding, right? So we can seamlessly use Haskell definitions, Haskell types, Haskell functions. Here this is just the normal Haskell integers and the plus from Haskell. And also notice that we don't have these explicit clock annotations. So there's no theta here that we have to put in here. So it knows that we have to delay according to the clock of this delayed computation XS. All right. This is a very simple example. Some more examples. Here's the map function, right, where we want to map this function from A to B and apply it to a signal of A's and then get a signal of B's like this. The only difference here is that you have this box here that I haven't really told you about. Now this is essentially the always modality from temporal logic, right? So intuitive makes sense, right? If you want to apply a function from A to B at any time in the future, you have to make sure that it is always available. That's the idea here. That's the map function. We also have dynamic switching, right? So that when you have a signal first behaves like another signal, like the first argument here, and then at some point in the future, you want to switch behaviors to a different signal. And that's the second argument, right? So this is the delayed signal. So as later, we get a new signal. And as soon as this new signal arrives, we switch to that signal. So that's how the switch works. And it also uses a language construct that I haven't really introduced yet. It's sort of like advance before, but it takes 2 delayed computations as an argument and sort of synchronizes them. But I don't want to go too much into details about that. I want to talk more about the how we actually implemented the language. So how do we pull this off? So as I mentioned, it consists of 2 components, right? So it has on the one hand it has the Haskell library and then a plugin for the Haskell compiler, right? But before I go into the details, I have to take a step back and tell you more about where do these clocks come from, right? So this again, this picture about our reactive program that receives inputs from these channels at the top here, right? We have this kappa 1, kappa 2, kappa 3. So that's how we name our input channels from which we receive our inputs. And now clocks are simply sets of those input channels, right? So here, for example, we have this clock here. This is a clock consisting of kappa 1 and kappa 2. And intuitively, a clock ticks whenever we receive input on one of these input channels that are in there, right? So this clock here will tick whenever either kappa 1 or kappa 2 will receive a new input, right? And you can think of these clocks as telling us when to update our signals, right? So this says here, oh, this signal here needs to be updated whenever we receive a new input from kappa 1 or kappa 2. So that also ensures that our program sort of self-updates its dependency, right? So if we look at what this type actually means, sig or float, right? What this actually means is, if you unfold the definition, it means it consists of the current value of a floating point number, but also the clock, right? So it's a delayed computation, which also contains a clock that tells us when to update this signal. And that's exactly this clock down here. It says update this signal whenever we receive new input from kappa 1 or kappa 2. And if this graph here, this data flow graph changes, the computation updates this clock, right? So it's because it's part of the value, right? Remember, a delayed computation is both the clock and the actual value. So this will update here. And also might update here if we get this dependency, it updates like this. Right? So this is where the clocks come from. So let's see how we implement this in Haskell, this idea. So this is the implementation of the later modality. I hope this is visible. So I've grayed out this part over here because this is not actually visible to the user. The user will only see, oh, there's a type later, right? And so a value of type later A consists of 2 components. It consists of a clock, which is simply a set of channels, and it consists of the actual delayed computation, which is a function that takes an input value and returns the actual value of type A. And then an input value, you can think of this as an input value that comes in from one of the channels from the top, right? So it has its channel ID, so which of the channels it is, kappa 1, kappa 2, and so on, and the actual value that has come in, right? And this way we can sort of thread these inputs that come from the top to the actual delayed computations at the bottom. But this is not actually visible to the user. The user only sees this implementation, so delay in advance. So this is just the syntax that the user sees. So it's just a function from A to later A and vice versa, right? But here we don't yet check the typing rules, first of all. And second of all, it's just a dummy implementation. It's just defined as undefined. So this will just crash if we actually run it like this. So what happens in the next step is that the compiler plugin will jump in and actually replaces these with the real implementations of them. Right? So this is the program elaboration part of the plugin. Right? So on the left-hand side, we have the surface syntax that the user sees, and these are then replaced by the implementation. Right? So this is the constructor of the later modality type with the clock and the delayed computation. And similarly, you have a corresponding advanced function that does the actual implementation, that sort of applies the function that will then produce the later value, the delayed value. All right, and so what the compiler plugin will do, it will see this definition of our increment function we've seen a couple of times by now, and it will replace it by this. So it has clock inference, so it will find out that, okay, this delay is must be with respect to this clock of XS, and it will replace the body here with this function that takes the input as an argument, and then will pass it on to the advance. So it does the passing on to the input values to the corresponding places where we call advance. Right? And we know this is always possible because of the typing rules of Async Rattus. All right, that's basically how the language is implemented. So just where does this actually all take place? This is a very simplified overview of the Haskell compiler pipeline, right? So it takes Haskell source code parses it to an AST, then it type checks it, then it desugars it to this intermediate language called Haskell core, does some stuff on this, and then this is very much simplified, generates the executable. There's a lot more going on, but I'll just abstract from that. And so what our compiler plugin does, it adds some additional phases here, right? So we have, in particular, we have this additional type check, where we check the stronger typing rules of Async Rattus. And then once the AST is desugared to Haskell core, it's a much simpler language. We do this elaboration and clock inference, right, where we replace those dummy implementations of delay and advance with the actual implementation and insert the clock information. And finally, Haskell is a lazy language. Async Rattus very much depends on being a strict language to actually have the memory properties. So we have to do a pass to turn it into a strict language. All right, to wrap up. So what I've shown you is sort of a first implementation of a synchronous modal FRP language, right? So a language that uses modal types to build asynchronous function reactive program. And also, in order to implement it, we had to use this program elaboration. I haven't seen this before, sort of using a compiler plugin like this for program elaboration, which works out very nicely. There's also a bunch of related work that I want to shortly mention. So this works. The underlying calculus on which this work is based is this async rat language. So if you're more interested in sort of the language part of this, have a look at that. And then secondly, it uses a lot of the implementation techniques of this Rattus language, but this is a sort of a synchronous language. So what we added here is all the program elaboration. That's sort of new in Async Rattus. And finally, there's this Lambda widget language, which is the first asynchronous modal FRP language I'm aware of. So a lot of the ideas of Async Rattus sort of also drawn inspiration from Lambda widget. But Lambda widget does a lot more things. So it also has linear types to build GUIs, right? So represent sort of this kind of manipulation of state. Okay, to wrap up, if you want to play around with this, so this is very much intended as sort of a test bed to try out this language. How can we actually build systems using modal types? How can we build GUIs? How can we build interactive systems? So you can try it out. It's available on Hackage. You can also find more examples of how programs look like in this language. So check out the paper and also the repository. There's loads of more examples of programs that use Async Rattus. Thank you very much.
thank you very much. We still are good in time for questions. Yes, I'm coming.
Hi. Could you say a bit more about this, the mismatch that you mentioned between laziness in Haskell and strictness in Async Rattus?
Right. So, yeah. So Async Rattus has to be a strict language, right? We want to. So the idea is that we want to evaluate as soon as possible to avoid space leaks, but also we have to make some parts of the computation lazy, right? The delayed part, right? And so we have to turn the lazy code into strict code, basically, right? So we, as part of the of this compiler pass here, what we do is we insert. So now we're getting a bit into the weeds, but so basically we have to make sure that all arguments for function definitions are evaluated as the first thing a function does. So we make sure that all function definitions in Async Rattus are strict, right? This is not sort of 100% sure, right? Because you might still be able to use functions from the Haskell library, right? So we do an additional check. So we make sure that the user can only use types that are strict, right? So whenever we use sort of a lazy map, then the system will throw a warning to you saying, you're using a lazy data type. Be careful, you might introduce memory leaks. So that's sort of the story of how we deal with strictness. So in a way, Haskell is an odd way to implement this language because it is lazy by default, but it has this nice infrastructure of these plugins. So it would be interesting to see how we can do this perhaps easier in a different language that is sort of strict by default.
I was a little curious about your implementation. You had this input value type, and on your slide it sort of existentially quantified over the type of the data. So how can you actually look at it? Is it actually more complicated in your implementation?
Oh, there's an unsafe course.
Okay.
Yes. Yes. So we rely on the fact that we hopefully have implemented the type checker correctly. So that we actually, because we know if the type checker is correctly, then we know that this will be the correct type.
Okay.
Thanks very much. So, could you go to your definition of map?
Yes. Yes, there we go.
Right, so there's this pattern here where you delay something, then apply a function, and then do advance on the argument. That's also often called map, like dmap. So could you define dmap as doing delay, your function argument, advance, and your other argument?
So can you say dmap again?
Dmap. So dmap of f and x is delay of f of av of x. And could you do dmap
so
of f?
On a delay, I mean.
Sorry?
So on a delayed computation? Or
Well, you've got this pattern, right?
Oh, yes.
You take your argument, you do av to it, then you apply the function, then you delay it.
Oh, yeah,
Right?
yeah.
Right. So could you turn that into a higher order function, and does that work?
Yes, you can do that. So that you apply f to a delayed computation like this.
Well, an advanced computation, I think, and then you delay the result.
That's right. I mean, but the XS here, right? So this XS here, this is delayed computation, and then you move this computation into the future. You say, okay, this computation happens in the future, right? And once we arrive in the future, then we advance it. Sort of we pull it back from its delayed.
Right.
Yes. I'm not sure what you mean by dmap here.
So literally, dmap or circle map of f and x would be delay, apply to f, apply to advance, apply to x.
Yes, so that you have that you take in a later of a here as an argument.
No, I don't want to change the type of map. I just want to rewrite map. I want to factor out that doing of delay in av. So I write that as a higher order function.
Oh yes. But you have to be careful because if once you delay this here, the app, for example, right, and so we want to do something like an applicative action, maybe, right? That doesn't work because if you have two delayed computations.
Why are there two?
You have to somehow delay f into the future, right? You want to say, okay, this f, I want to have it in the future, so that in the future I can apply it to my ss.
So all I want to do here is the simplest kind of textual refactoring, right? So I've got this pattern, I apply delay, I've got the thingy, I apply adv, I've got the argument.
Yeah,
right? I want to
that's possible.
refactor that into a higher order function.
Yes, I think that's possible. Yes, and what I was saying is that this is essentially a map that now works instead of working on signal, it works on the later. Later A. And then I can use that in the definition of this map.
Yeah.
Yes. So short answer, yes, you can do that. But it only works in this setting that you have an f that has this box modality, so that it's available always.
Yes. Right.
And then you can apply it in the future or any other future.
Right.
Yes.
Okay, and you mentioned that the rule, right, if x of type A appears in gamma, then x has type A, that you can't use that rule. So how did you have to change it, and where does that show up in your implementation?
Right, so this is the typing rule that I've why do I have this? So this
Because the next slide, I think you have the rule you didn't have.
I haven't shown the introduction rule for variables. But essentially what happens is here, right? So when we delay, we introduce this tick into the context.
Yeah.
Now what this essentially means is all of the variables in gamma, they are now one time step older. So this basically says one time step have passed. And now the variable introduction rule says you cannot use those things in here anymore because they're too old. Right? But you can get access to them again because, as you see here in the advance, we sort of remove the tick, but we also remove the gamma. So now all of a sudden, the things that were inaccessible over here are now accessible by having removed those. Right? So these ticks in the context, there's sort of time barriers that cordon off some of the variables from use temporarily. Right? So that's how they occur. That's why we don't have, in general, this rule, right? Because even though we might have an x in our context, there might be to the left of a tick, right? That tells us, oh, this variable is too old, so it might.
I see that the check for that shows up in your scope checking.
Yeah, exactly. That's exactly right.
Hi, I'm returning to the question about strictness and laziness. So you implemented that as a plugin. What's wrong with using strictness annotations?
There's nothing wrong with it. I actually changed to that now. So this is an old picture, but now on the latest implementation, I actually did change to strict. One thing that is not so good with this, just a strictness language extension is that it sort of works on the whole module.
Yeah.
Right, and I might still want to have a module where part of it is Async Rattus and some part of it is still normal Haskell.
Sure, so there's the extension that makes the entire module strict, but there are also strictness annotations you can apply to particular values.
Yes, you can do that, yeah. Right. But then the programmer has to write them, right? And I don't want, I just want to have sort of idiomatic Haskell-looking code that just is interpreted as, oh no, now we are in strictness land of Async Rattus.
And I was wondering if there was a way of making those strictness annotations be solely in your library so that forces values as far as you're concerned, so the user can still be free with what they want to do.
Yeah, but the user might still write functions that are not strict, right? And then pass them on to map, right? And then we run into problems.
And then I was wondering how this would relate to multi-threaded programs. Does it work?
Yeah, I mean, yes, it works, right? So in a sense that you can use this model for a very sort of simplified version of concurrent programming, right? Where you have concurrent values coming in from these inputs, right? And then you have to interact with them, right? So but it's a very sort of particular. So it's not a general model for concurrent programming or parallel programming.
Yeah, I guess I was concerned about having a kind of stop the world going on your clock synchronization, as well as the stop the world going on for garbage collection and how that all interacts. I don't know if that's.
I don't know.
Yeah, thanks.
Hi, I have a question. What happens if there's a type error in the custom type checking pass that you implemented, do you have to generate your own type error messages, or would this be caught in the previous type checking pass?
Yeah, we sort of you can. It's very nice. Sort of the compiler plugin API is very nice. Allows you to give error messages. You just give an error message and give here's the position information, and it gives you very nice output as if it were a normal Haskell compiler error message. So I mean, it might not be of the same quality, but at least at least sort of you get the same kind of integration with the IDE and so on, right?
Right. So
and they're also at the level of the source language, so they're not as sort of given as on the level of the intermediate language. So it has at least the hope that we can achieve good error messages.
Okay.
The setup.
Yeah. Thanks.
Yeah, thank you again for the great presentation and the discussion. We are 5 minutes into the coffee break, so